It's funny. Okay, so today we'll be working on some path integration, and we'll be laying the groundwork for that, and we'll also possibly touch on antiderivatives. So last we left off, we had done some power series and exponential growths. We had found out that measuring exponential growth using this function here, defined here, which is sort of like a root test on each projection. If we measure exponential growth like that, it has lots of different nice characterizations like these, and all sort of the standard proofs that you would expect. So if you multiply it by constant, it's the same. It's sort of a monotone function, so monotone mapping. It's subadditive. It's also submultiplicative. And we can use it to characterize the convergence of sums, similar to the summation of a geometric series. In fact, exactly like that. We used these to prove, also with some special, induction here, with these special steps. We used this to prove that if we have any series of repeated products as sort of an exponential sequence, then its exponential growth is just the absolute value of the first projection. We use that to then characterize power series using this and the previous result on the convergence of summation. So we're able to characterize the convergence of power series this way, and we found out that the convergence of a power series, so we found out that the convergence of the power series is just dependent on the first projection. We had proven that, in fact, that domain of the first projection is just this first. It's just a pre-projection of sort of a complex disk, just sort of a disk on the complex plane, where the radius is determined by this phi function, and the center point is just the first projection of x naught, which is the sort of this term in our power series. We found out that these power series are differentiable, and we found out that the derivative is just sort of the standard expected derivative, and using that we were able to prove that the Taylor series representation. So if you have any power series, you can take as repeated derivative using these formulas, and by just sort of doing the correct derivative, you can find out that the the nth coefficient is exactly the nth derivative divided by n factorial. So that's sort of the Taylor series representation. That's also enough to prove that that the coefficients in a power series are unique to the function itself, since the coefficients are conversely determined by the derivative. So that was what we did last time. I don't remember if we had done this degenerate case. I think we may have done a little bit of it. Over the weekend, I went and sort of spiffed up these proofs. I don't think I wrote any new proof, but I don't remember also. I think the only new proofs possibly that we have is that we have this, which is regardless of what our alpha coefficient sequence is, if you just have the first projection of the x, which is sort of the base of the exponential, if that's 0, so if it's not a unit, then the phi value, when you multiply it by these repeated exponents, defaults to 0. So this would normally, this calculation, if alpha had an infinite phi value, this calculation would not be definable using our multiplicative, our submultiplicativity property. But in this specific instance, it just happens to be 0. That gives us that power series will always converge when their input is directly above, quote unquote, so the first index, the first projection is 0, when it's sort of directly above the center of the power series, above or below. We have a little proof here that if you just restrict the domain of your power series to these values, which are guaranteed to converge, then it's also differentiable, and it has the exact same derivative formula regardless of what the coefficient series is, the coefficient sequence. It's sort of a really similar proof. We basically just use this C function to show that all the lower indices of these remainder, of this whole remainder term, end up being eventually 0. But that's really interesting to me, because regardless of the coefficients, there will always be this this set, and this has quite a lot of points in it. There will always be this set where it's differentiable, and in fact, given the Taylor series representation, this sort of theorem, which shows that these coefficients are unique, you can actually recover just using this small sort of thin slice of the total space. You can actually just use that with derivatives to recover the coefficients. So that's pretty interesting. This doesn't really get used in anywhere else, but it is sort of an interesting thing to see. Okay, so now we've got integrals is what we're going to be working on next. So in order to define, so we'll be doing path integrals. So this is similar to in complex analysis, there's a notion of path integration. You'll have some path which has the domain of, it'll be a function with a domain as being the unit interval, for instance. It'll have the domain being the unit interval, and its codomain will be sort of a smooth continuous curve. And you can then integrate on that using the substitution formula. You could also define it as using the Riemann integration sum. We'll define ours in terms of the substitution formula, though. So we'll say, so we want to start by defining our integrals in terms of paths. So we'll say, how do you want to start this out? So we'll define contours first. That seems to make sense. Okay, so Okay, so you want this to satisfy several sort of continuity conditions. Is the final goal one big result with smaller results as an ancillary benefit along the way, or is it the smaller results that you're aiming for? That's a good question. I think the original intent of this paper was to essentially provide a framework by which you could do all of these calculations and use these higher order functions that previously are not available. My original intention was to be able to use these results essentially. If I wanted to, for example, if I wanted to quickly know that if I have, say I take the Riemann zeta function, and then I take e to the power of the Riemann zeta function, so I compose it with the exponential. What sort of function is that? One of the things that one of the theorems, and this is a bit of a spoiler for the future, although I would send you this first draft if you just asked. So one of the eventual results we use is down, right here. So this result, it's reliant on a whole bunch of other things, but essentially the result is saying if you have a complex analytic function, it's complex analytic at so you've got a point in our space A, and in fact it's bounded, this A sub theta, we'll get to this eventually, but it has to be bounded growth. So essentially what we want to say is we have some point in this space, and you can actually think of that point as sort of a Dirichlet series. So we can look at those real quick actually, so this will make sense. Right up here. So if we have a point, a coefficient sequence C, we're calling it, and as a coefficient sequence, we're actually just considering it as a point in A. So remember, the points in our structure A are arithmetic functions, so they're just functions with domains being integers. So you can think of them as a sequence of coefficients. The Dirichlet series with using coefficient C and the variable S is this sort of summation. So it's a sum across all the positive integers, which remember that's the domain of our points. That's sort of the domain of all of our projections. It's the summation across all these indices, and we take the nth projection and we multiply it by n to the power of negative s. So for example, the Riemann zeta function is one of these, where the coefficient sequence is just all ones. So you can sort of consider the zeta function as, and so this would be called a generating function for our points. The set of A sub theta, this is just the set of whatever C coefficient sequences. It's just the set of whatever coefficient sequence where the summation converges somewhere. Because of course, if the coefficient sequence occurs too quickly, then this will never converge. So it's just the A sub theta is just wherever they converge somewhere. Anyway, so if you can consider the zeta function as one of these, and you might want to ask what'll happen if I exponentiate the zeta function. That would give us a new function, but what kind of function will it be, and sort of how can we reason about it? Actually this is the last theorem of my original draft. I mean, there's some other stuff, but none of that's important. This is sort of my last theorem of of my previous draft, which is that if you have any function f which is complex analytic at the first projection, so the first value of this C coefficient sequence, which to remember is just a point in our space A. If you have any function f which is complex analytic at the first projection, if you apply that function with the Dirichlet series with coefficient C, it's the same as taking the Dirichlet series, but where the coefficients are f of C. So remember, as a complex analytic function at C1, we can express it using a power series, using its complex analytic representation, and then that power series will converge in our more extended general space. And we remember, it's only the first index, it's only the first projection that determines the convergence of a power series. So essentially what this would be saying is, for example, if f were the exponential function to exponentiate something, exp, the natural exponential, and our d of c was the zeta function, then this would be telling us, if we exponentiate the zeta function, we'll get another Dirichlet series, where the coefficients are the result of exponentiating whatever the original coefficients would be. So sort of in practice, for example, what this would eventually look like is that we could say, something like, let zeta be this point. So this zeta symbol would just be the sum of all these basis vectors. So of course this would be 1 on every projection. And if we set it up like that, then we're saying d of zeta with s is just the zeta function, zeta of s. We could possibly use a different symbol, but this is essentially what would happen if we did that. And so the theorems we're building up to is that if we have a complex analytic function, for example, the exponential, yeah, so this would be d of, so this is d of zeta with s So what we're building up to is something like this, that eventually we're going to end up being sort of in this configuration. So this would be, if we take e to the power of zeta, then this is the same as the sum across all n in natural. We have n power negative s, and the coefficients are the nth projection of e powered zeta. So it would end up being, so essentially this would be one of our eventual results. The more, of course, since the more general form, it applies for any, analytic function. By laying the groundwork to use all these analytic functions and higher order integrals, there's just a lot more you can say about it. It becomes a lot more easy to say things like that. So this is one of the things we're building up to. All the theorems along the way are sort of supporting that. You could probably prove this specific result not too difficultly. It might be a little bit of a hassle, but it wouldn't be all that hard, to be honest. You don't really need all the framework to get to this result. You also don't really need all the framework to get this result for every complex analytic function, so long as it's analytic at in this case, it has to be analytic at p1 of zeta, which would just be 1. So if you have some function which is complex analytic at the input 1, another function which is complex analytic at the input 1 is the natural log function. So for example, our eventual result would also be proving something like this. So we would also be proving something like this. And of course this would apply for it doesn't have to be natural log, it doesn't have to be exponential, but that's sort of one of the things we're building up to. So we're showing that there's a natural way to interpret these complex analytic functions. We also show that there's one of the things especially that we want our integration for is actually we're going to prove that if we have a particular sort of domain for a function, and that function is differentiable, then actually it's analytic. So this is actually an extension of the analyticity of holomorphic functions, which is a theorem in complex analysis. So that theorem says if you have a function with a complex domain, so that's a particular type of connected open set, then actually it's an analytic function, which means every point has a Taylor series which converges to the function in a neighborhood, a non-empty neighborhood. So one of the things we're going to work up to is something like that, where as long as you have a differentiable function, then actually it's analytic, so long as the domain has a certain condition. And actually the condition is a little interesting, but we'll see what it is. Actually, I haven't written the full theorems for what we're building up to with integration. Originally, I used just open sets in our topology, but you actually don't need a condition quite as strong as that, which is what we'll be doing. That's especially not necessarily in this section. We'll be building up to it in this section, building all the tools for that. But that just gives a lot more power. Knowing that, for example, because power series are differentiable, that'll tell us that power series are analytic. So earlier we were talking about, we could show that a power series is analytic by showing, a particular formula has some convergence to the function. We could do that. And it would definitely be serviceable. It would show us that if we have a power series, that this is generalizable to an analytic function. And that, in particular, that gives us identity theorem. So identity theorem is a consequence of basically just power series being analytic functions. So long as you have a power series being an analytic function and infinitely differentiable, and you have the Taylor series representation, so long as you have all of those conditions, you get this identity theorem, which basically states that if you have two analytic functions on a connected set and they agree on an accumulation point, so they have a whole bunch of points where they're equivalent, and there's a limit point that's inside the domain. If you have all those conditions, then actually the two functions are equivalent. They're equivalent on their entire domain, which is very nice. That's going to help us essentially import complex analytic functions into our space. So we don't actually have, so these functions like this exponential or this natural log, we could say, define, for example, natural log of, x is defined as, we'll say like 1 minus x is the sum, and from 1 to infinity, 1 over n, x to the n. So we could say define natural log using this Taylor series representation for any x for which this converges. So especially, if the first projection has a magnitude less than 1, then this would converge. We could say define natural log using this identity. But what if we wanted to use a different identity? Or for example, what if we wanted to take the natural log of something where this doesn't converge? How would we do that? Or what if, for example, I wanted to say, the natural log of, x plus y is, x times y is the natural log of x plus the natural log of y. What if I wanted to say something like that, but to have, x and y be arbitrary points in our space, or maybe not an A, but an A star or something like that. Just some other points that aren't just complex numbers or real numbers. What if we wanted to do something like this? Well, if we only have this Taylor series, we can't. It's impossible. There's no way to do this. Maybe for some limited points, like for example, we know this applies for certain complex numbers, but they would have to be complex numbers which are sort of stuck in this thing, in this region. Maybe we could manipulate this power series to prove this identity. But instead of that, which would be really hard, and it would only work, right? It would only work for this one function. We would only get that property for natural log. Instead of doing that, if we can prove analyticity, then we have identity theorem. And actually from identity theorem, it's very quick, right? So from identity theorem, suppose we've got, suppose we have the identity x, this identity up here for some domain. We'll just call it, S. Actually, we'll go a little simpler. Let's say we have this identity, for x and y in the image of the projection of S. So S is some set, So S is some set in our wider space, and we'll pick points x and y in its projection. And suppose in this projection we have this rule that this ends up being true. We do know that, for example, there are complex sets, in particular the positive reals, where this always applies. Well, if S happens to be a connected set, then we could say, okay, well, let's interpret both sides of this equality. Let's consider, what if y is fixed, and we'll just consider this as a function of x. Well, both of these you can prove pretty quickly. So this, from the sum rule, this is a differentiable function. Is an analytic function, in fact. If natural log is analytic, then this summation is analytic in terms of x, so when y is fixed. Likewise with this left side over here, this is an analytic function. If S is a connected open subset of the complex numbers, or sorry, if the P1 of x is an open connected subset of the complex numbers, that's an accumulation point. We get an accumulation point. And because we have this equality on an accumulation set, and because S is connected, then we would get that this equality actually holds true for all x with that fixed value of y. So if you keep y fixed, then this holds for all x. But this works for any y, right, in P1 of S. For any y, for any fixed y in P1 of x, this identity holds true for every single x in the S set. So then we can just do the other direction. Take any x, take x as a fixed number in the set S. We know that for every y in this projection, P1 of S, that this identity holds true. Consider the left side and the right side as functions of y, where x is fixed. They're both analytic. They agree on an accumulation set, and S is connected. So this actually holds for every value y in all of S. And then you're done, right? And then so long as you have this in this projection, P1 of S, this complex set, then you actually get it for all of them, just using identity theorem. When we go to prove that, we would have to sort of, say explicitly, this is what we're doing, because this holds and this other thing holds, then you get this. You can do the same thing with exponential, right? So if we just define exponential as its Taylor series, something like this, so we'll just have n factorial x power n, something like this. So we do know it's not too difficult to measure that this will converge everywhere, even if x is just in our A set in general. Using this definition and the same technique we did up here to prove that, so long as you have this in some small set, that you get it so long as you have it in this projection, then you'll end up with it in the whole set. You can do the same thing here for exponential, to say, exp of x plus y, well, that's just exp of x times exp of y. And so this is another thing that we're working up to. And you don't have to go through the power series representation to prove this identity. Both of these functions, these are both analytic functions of x and y, respectively. Well, we don't know that quite yet, but we will know that. We will know that these are analytic functions of x and y. And just using sort of the same trick, fix x in the complex plane, and then use identity theorem to prove it for all y, and then fix any y, fix any y and take x in the complex plane. Well, this will hold there, because we already proved that. And then we can just generalize to all x in this whole set. And that's sort of the trick. So that's what we're building up to. So things like that will be really easy. So you won't have to pass through. So just knowing that, having a power series representation makes your function analytic. Just knowing that is very powerful. And so that's sort of what we're building up to. And all of these tiny theorems, they're just useful. I have no idea what anyone else will do with any of the other, results we conclude with. Hopefully that somebody will like them. Or get some use out of them. But yeah, we're just building tools to have So if we ever need to use these tools, they'll all be there, and they'll all be, you know, nice and laid out. And hopefully anyone who wants to use these won't have to do too much work to get them to do what they want. So that's sort of our goal. Okay, so so we want to define what a so we want to define what a contour is. So what sorts of curves are we going to be allowing to exist? So let me think. So we want so what we're eventually going to do. So I guess I can lay this out in advance. So we're going to eventually have is something like this. So we'll have this is this integral from 0 to 1 of f of sigma t, and then sigma prime of t. So eventually what we want to build up to is with our definitions, with our definition of contour integral. Yeah, very cool. Yeah, so that's sort of what we're building up. Oh, sorry. Yeah, that's sort of what we're building up, and hopefully it'll be nice enough that people can use it really easily. Give me just half a sec. Okay, sorry about that. I had to fix my cord. Yeah, so eventually what we're going to be, so what we want to do with these integrals, so we want to have a path integral, so some path sigma, and we'll have some function f, which is defined over that path, and we want it to satisfy this equality. So if we integrate across this path sigma, it's the same as integrating from 0 to 1, so just a standard, you know, line integral of f of sigma t multiplied by sigma prime of t, dt. And of course, this will have to satisfy another definition where we'll want to have, you know, for any projection, we essentially just want this to be linear with our projections. So it'll be pointwise, essentially. So this is sort of the definition that we want to build up, and we could actually probably sidestep the problem of defining a contour sigma by just saying, you know, for any contour sigma mapping the interval to A, which is continuous, which we can just say, you know, let it be required to have all these things be defined. We could probably try to say something like that. That might not be what we want to do, because that would be just saying, you know, required to have each of these be defined might not be super helpful, because that's a little vague. What we can do instead is we can say, well, if we work out, you know, this projection, right? This is a projection of a product. We have f times sigma prime. We could work that out as a sum, and then each of these projections, sigma prime, would be, you know, some projection of f times some projection of sigma prime. So it'd be a finite sum of those products. And if we want, you know, to require f, you know, for any reasonable function f, our curve sigma has this property. Really what we want is for sigma prime, each of its projections to be, they should be integrable. Is really what we want, and they should also be continuous. So they should be continuous and integrable. So really what we want is sigma should be, so we have a function, so a contour is a function sigma, which is, and we should say, is we can say, which has each projection p sub n sigma, or sorry, we can say is continuous, and for which each projection p sub n of sigma is piecewise differentiable. So this is sort of a piecewise differentiable curve. This is, I believe, how a complex contour is defined. We can actually look that up to see, you know, how do they define these. I think they define them as smooth. A continuous function. Smooth curve is a non-vanishing continuous derivative. We could probably try that. That might be something else we could do. I'm not actually sure to what extent having a non-vanishing derivative is going to be possible for us. So in our case, the lots of our results are essentially extensions of sort of, you know, different results from real and complex analysis. But the notions of whether or not something needs to be zero or whether or not it needs to be a unit, those two different ideas will sometimes get replaced in different contexts. So sometimes we need it to be a unit, but sometimes it's just enough to not be zero, so to just not be the additive identity. Sometimes that's the case. Like for example, so we do know that there's a lot of cases where we need something to not be a unit specifically. So for example, we know that for a division to always be defined, it has to be a unit. We also know that for the reciprocal function, so that is the division, that needs to be a unit, we have all power series are sort of dependent on that's down here. All power series are dependent on the first projection, which is essentially the defining feature of whether or not it's a unit. It's just sort of the importance of the first projection. But there are other cases where it just needs to be zero. So up in this differentiability section, I have a lemma here. So here, if a function f is differentiable at a point and its derivative is not zero, then there's a neighborhood of that point in the domain over which any different point y has f of x not equal to f of y. So this is not quite the same as local injectivity. It's almost the same as local injectivity. It's not quite the same, but instead what we have is sort of a each individual point has a neighborhood where it's not equal to where its image, its evaluation is not equal to any other evaluation in that neighborhood. So this essentially this condition is just saying we just don't want the derivative to be zero. It could be a non-unit, and this would still apply, but it just can't be zero. So that essentially comes from the fact that it's zero is the additive identity. It's what you get when you subtract something from itself, as well. So these are sort of something that we have to sort of work around when defining what we want a contour integral to be. We may not necessarily be able to say that it's always non-vanishing. That might not be enough for us. It might not. It depends really on what different theorems are using these for. Whether or not they're, they need to be non-zero or they need to be a unit or what. In any case, essentially the way that these are built up is we have let's see. Smooth curves are, smooth curves are injective continuous curves with non-vanishing continuous derivatives. What we can do, we may not need to be continuously differentiable, but I think what we do need is that these are piecewise differentiable with a integrable derivative. If we said we could upgrade this to have a continuous derivative, piecewise continuously differentiable. It's unclear to me whether or not we require that, but we can just update the conditions as we go forward, if we would like. So okay, so what we have is so we can say for a function, let's say okay, so we can see something like this. So so we've defined our curve, which is, it has each projection, P sub n, as a piecewise differentiable function with an integrable derivative. So its derivative has to be, and actually we can maybe go a little further. We could say that the projection is not just an integrable derivative. We can maybe we might want to say has bounded variation. We could alternatively just we could probably really just upgrade this to do continuously differentiable. Yeah, actually that makes a little more sense. Okay, I guess we'll just go with that for now. It's not that big of a deal. This is definitely, this is a lot weaker of a condition than having sigma itself being piecewise continuously differentiable. Technically, we'll have sigma may not be differentiable anywhere. It's unclear. I actually don't know. I think, let me think. Given that a piecewise curve is has only countably many, in this case, finitely many points of discontinuity, and given that we have countably infinitely many projections, this should end up with only countably many discontinuities of its derivative. So actually we can point that out. So we'll say, so we'll just sort of notice that this is differentiable on its whole domain, except possibly countably many points. So, so we've sort of given ourselves these. So given these, given a function defined over the image of our curve, such as f, which is mapping the image of sigma to a, we can define a path integral of f over sigma using the substitution rule. and we'll sort of define that as this. So we could define it like this, or we could say, let's have this defined as equaling, we can say, instead of defining each projection, we can define it like this. This might be a little involved. I think this is okay. So essentially what we're saying is that for each index, we're defining this as the summation of these p sub n, so and so. I think that's okay. Yeah, so we'll leave it like that. So the first thing we probably want to do is to actually just prove the substitution rule, just itself. So the substitution rule is, if I can remember this, something along the lines of, well, it's essentially this, right? We have integral of sort of a composition of curves, like something like this, and then a function f of x dx and I forget, let me think. So if we want to put, I think, sigma in here, and then we'll have just gamma. And I think this is how that goes. So let me do a think on that. So we'll have sigma and gamma being contours, and so essentially we're doing f of sigma of gamma. I think that's correct. Yeah, I think this is what we want. Okay, so we'll say let something like that. So I want to say something along the lines of some definition of what it really means for a function to be integrable. Actually, maybe we should start with a theorem actually on that, which is, we'll say actually, let's say this. A function f is integrable over sigma. I think I want to say something like this. So f is integrable over sigma, so long as each projection p sub n f sigma t is an integrable function. So we can also put this into as a definition, instead of a theorem. If this were to be a theorem, then the way the above definition would work out, so it would essentially just expand the summation definition. And we would say, well, this is just a finite sum of some products. And if each of these projections are integrable functions, given that sigma, the sigma prime, each of its projections are continuous, piecewise continuous, then each of its projections are integrable, and then an integrable function multiplied by an integrable function would be integrable. And so we can actually, so that would be, I guess we can just sort of do that explicitly. We could state this like this. And that would have, I think, a pretty short proof. So yeah, okay, so we have okay, yeah. So using our definition of integration, we'll have for each. Actually, yeah, we can actually just sort of work this out. So the integral of 0 to 1, we have p sub n f of sigma of t times sigma prime of t dt on the outside of the projection. Where did the other parenthesis go? Oh, it's over there. This sort of integral here, this will just be sort of a repeated summation. So I'll have sum of, we'll do d as a divisor of n, and we'll have, actually instead of d, we'll do ab equaling n, because that's a more compact way to notate that. So we have p of a, f of sigma t, and then p of b, sigma prime of t. And we might want to rearrange these, actually. So put this on the left side. And then on the left of that, we'll pull out this summation. So I'll just pull out this sum right out. Okay, so that's the first step. So we'll say, since each piece of n, let me actually just copy that. Okay, so what we're going to do is we're going to say, we've set up the sum. I'll format it in a minute. So we've set up the sum, and what we're going to say is fix some index n. Then for each divisor, a as a divisor of n, we have this projection, p of a, f of sigma t, as an integrable function. This is integrable. So this is by the premise of the theorem. So each of these projections, f of sigma t, is integrable. Also, for each divisor b dividing n, each projection p sub b of sigma prime t is piecewise continuous, and therefore integrable. Especially since, we just have a bounded domain. So we have the products of being piece of A, piece of B being integrable, and consequently the summation well, this will be okay, yeah. So, so each piece of B of sigma prime is integrable. Our piece of A of f of sigma t is integrable. So the Dirichlet product, this should be piece of n, and we have f of sigma t times sigma prime t. That'll be integrable. Okay, that's nice. So each of these are integrable, these products. Then we just sum up these integrals. Well, by linearity of integration, we can build a sum in. This is just this piece of n projection of this product. But then this just means we just have each of the integrals of so each of these integrals is defined. piece of n of this sum oh, whoops, that's not right, of this integral So hopefully that's the last. We'll have to get too much into integrability of functions. So as long as each projection on this composition of this path is an integrable function. So remember, f just maps the domain of sigma to our A space. So f of sigma t is just a function just from the line 0, 1 over to this space. And then we're just taking this projection piece of n. So if each of these projections is integrable, then f is integrable over the path sigma. So that's sort of what we wanted to conclude with. Something else we can do, so we've defined the integral in this weird way with this summation. We can actually analyze this a bit more, so that we can just say, actually we can make a note here. Actually, I guess we can make it here first. No, let's do it one step at a time. Yeah, we'll go down here. Okay, so oh wait, that doesn't make sense. Oh gosh, let me think. I think it's supposed to be the outside for this substitution rule. So we want to have some composition. I think there should be well, let me just look up the general statement in our previous draft. I think what we did previously, oh yeah, let's just do that. Okay, so let sigma be a contour and f integrable over sigma. Actually, we can say integral on sigma of f is just the integral on let's say f sigma t dt times sigma prime And we should say, how should we express this? It's saying I don't have. Where's the error? Well, let's just pull this apart piece by piece. Oh, there it is. Little typo. Okay. L of t is, we'll do actually just t, I think. Yeah. Okay, so this hopefully should not be too complicated. So essentially, this is essentially the sort of the substitution rule, more or less. What we want to do is we want to say, essentially we just want to compare these on all of the projections. Okay, so what we can do is we'll say for each index n, we'll evaluate the integrals on the piece of n projection. So the way this works out is, first we'll have f, the integral on sigma of f. This one, if we just do the piece of n projection, this is just this summation. So originally this is the summation. So we do this nth projection, and this ends up as, from the definition, we just get this, but we just don't multiply by the e sub n. So that's down here. This will be that. So that's that one. The second one, for this other integral on this L, this is similar thing, but instead, so it'll be a little different. What we actually have is that instead of sigma prime, we have L prime, which is 1. Instead of sigma of t, we have L of t, which is just t. But then instead of f of t, our function is f of sigma of t, and then we multiply by sigma prime of t, and that's the same thing. And then we're done. Actually, that's literally the proof. Yeah, so that's super straightforward. So over on this left one, we just expand the definition. Over on this right one, we just use the fact that the derivative of L, this L function is 1 that we've defined, this contour. And then it's just immediate. This derivative is 1, it just goes away, and then we just have the function over the contour L. So we just get this. So for convenience, we'll say we'll define this integral like that. A plus t times b minus a. Okay, so we're saying we're going to use this standard sort of line integral notation for our integrals, but what we'll define it as is whenever we take this integral, an integral like this, we'll just assume that what we actually mean is this line integral. So we'll use this line contour. It's just a standard. It goes from a to b in a straight line, from t going to 0 to 1. And whenever we write this integral from a to b of f, what we actually mean is this integral on this particular line. Yeah. So that'll be like that. Okay. Hopefully that checks out. Actually, before that, we can do another one. Okay, yeah. So we'll have sigma be a contour. What we want to say is if sigma is purely complex, then we can pull in these projections. That's what we want to say. So we'll say we'll have such that sigma of t is in C, or we can say the image sigma 0, 1 is a subset of complex numbers. Okay, nice. Okay, yeah, so our next is if f is integrable over a complex path, then for each projection, the projection of the integral is just the integral of the projection. And the way that we prove that is we just use the definition. So in definition of integration, we have the integral so we have p sub, so the first one, let's pull that out. The first projection, the nth projection of this first integral is just going to be up here we have this, where'd it go? Definition of integration. Here we have this n projection. And we can say okay, yeah, so we take this on projection, we get this, but we can actually just consider this as, because, so since, sigma prime actually needs to be a subset of the complex numbers, actually, we'll just say sigma, so yeah, maybe that's fine. Okay, so my prime is subset of the C, so yeah, so we do this projection, we pull this out, and then we should pull sigma prime out of this projection, because it's just a complex number. And then this is nothing but, we have sigma prime here, we have sigma here, so this is just the integral of sigma over a piece of n of f. Let me just get rid of this sigma and just do x. And we'll do dx here, because that's the variable we wanted to use. And that's the proof. That's very fast. So we can actually add, if we would like, we can add a corollary here. We can say where L maps T E identity. Okay, let, so we can say F, no, okay. Actually, I don't really want to say that. Okay, so all we've done is we've observed, so we've used these two theorems. So our first one is, there's first three. So this one tells us what sorts of things are integrable. This one tells us that we have this substitution rule, where this L curve is just sort of the identity contour on the unit interval. And then we're saying, on this third one, we're saying, let's suppose our contour is a subset of the complex numbers, so we're integrating over a complex domain. Then this projection pulls in, so integration is linear. Broad proof demonstrates, so this demonstrates that the integration in A is an extension of complex integration. In particular, just using sort of this notion. And so we have, right, so we have, in order to sort of utilize this, we define these linear paths, define this sort of linear integration point A to B. This doesn't conflict with the usual notion of complex integration. Now we can sort of go ahead, we're going to prove a whole bunch of linearity laws. Sorry about that. We're going to prove a whole bunch of linearity laws. So, we have, okay, this will be a little involved. In order to prove full linearity, we actually have to prove the linearity of cancellation. So that'll be an interesting thing to prove. I think we can do that. So we'll have a theorem. So and a constant, I'm going to say non-zero constant. So the integral on sigma of CF x dx and C integral sigma f x dx. Okay, so this one is actually interesting. In order to prove this, we have to use both the cancellation formula and also the Dirichlet product formula to prove this. So to do this, so we'll have, so first things first, we'll have, oh gosh, let me think. Let's actually go up. Okay. Where were we? This is this, this is that. Okay. F is integral over sigma even. Okay, so this. So we want to use, so we'll start with the product formula. Okay, so take the case that F is integrable over sigma, then we have B sub n of, we have CF sigma t. This is just the summation AB equals n of P sub A of C times P sub A of B of F of sigma t. And we'll just state each P sub, or rather, since each P sub B F sigma t is an integrable function, then P sub n of CF sigma t is integrable as a linear combination of integrable functions. And then we'll say since this applies for any index, for any projection, then CF is integrable over sigma. So we just assume that F is integrable, write out this P sub n product for C times F. We get this. This is just a linear combination of these integrable functions. So this is integrable. So all of these projections are integrable, so C times F is integrable over sigma. So now we take the converse direction. We'll use the cancellation formula for F is CF over C. And we'll just pull that from where it is, right here. This is our cancellation formula. And we'll put that down where we want to do a cancellation. That should be up here before the power series section. Right here. Okay, so we'll plug in this cancellation formula. And so what we want this cancellation formula to say is we're doing x will be CF and y will be C. So we'll do that plugging in. So x will be CF. We have x is CF, x is CF, and then y will be C. Y will be C. Y is C here, C here, C here, there, and right there. And then we can simplify these a little bit. So this C cancels C, cancels out, C cancels C, and I think that's all. And this y right here should be C. So let me double check that I've plugged all these in correctly. So we have F, C, C, not x's and y's, not x's and y's. Okay, we're good. And then we'll write, instead of just doing F, we want F of sigma of t. So we'll put that in just so it's clear. F of sigma t, F of sigma t. I think that's all of these. Okay, yes, so we have, right, okay, so since C is constant and each F will have each, right, okay, yeah. Induction, I forgot, always induction. Okay, so let me do that. Instead of doing n, we'll generally do k for projections. Maybe I'll go back and replace those in other places. And let me actually make a note of that. Okay. So as I was, so we have all this. Okay, so by induction, so across K, suppose each projection P sub K F of sigma of T, sorry, not P sub K, it's P sub A is integrable for A less than K. By the above formula, then we actually, yeah, we have written the projection P sub K of F sigma T as a linear combination of integrable functions if follows by induction that F is integrable over sigma. So yeah, so essentially for this, yeah, so for this reverse direction, essentially we have, so we're writing P sub K of F of sigma as this combination. So this is a non-zero constant, this reciprocal term. CF is integrable by premise. And then using this induction, we say, let's suppose all these lower projections for A less than K of just F of sigma is integrable. Then these PBCs, these are all just constants. So we have this linear combination of these and this one, of these integrable functions. So P sub K of F of sigma is integrable. But since we're just doing an induction across arbitrary K, this follows for every K, and thus F is integrable over sigma. So essentially what this, so these two directions are saying F is integrable over sigma if and only if CF is. So now we have to prove that these integrals have this linearity property. Actually, before we, yeah, actually this is fine. What we could maybe do, no, this is probably fine. let's leave that there. We'll come back to that in a second. That's to prove this second claim. So we've proven that they have this dependency of integrability. What we actually want to do first is actually prove additivity, because that'll be a little helpful, I think. So we'll say okay, there we go. So this is our linearity. So we want to show if f and g are integrable over a contour sigma, then so is their sum, and also the integral of the sum is the sum of integrals. To prove that, we just use, so first just notice that p sub k of g, rather f of sigma of t, and then we add, or rather we can say f plus g. This is just first with f and then with g. Right, so for each projection, these projections f plus g evaluated at sigma t. This is just the projection of f at sigma t plus the projection of g at sigma t. So f plus g is integrable over sigma as, or rather, each projection p sub k f plus g of sigma t is integrable as a sum of integrable functions, and consequently f plus g is integrable over sigma. So once we have this, to prove additivity, we use the additivity of complex integration. So we have definition of integration, or rather even we can just say use the substitution formula. So this will go from 0 to 1. We'll have to have sigma t in both of these. And then we want to extend this, sort of separate this out. So we'll have this integral of f with sigma prime of t dt, and then we add this integral of g with sigma prime of t dt. Let's make sure I got that right. Where is that? I'm not looking at it, it's right here. So we have sigma f plus g, we use the substitution formula, distribute and separate, And then we're actually going to need to separate these on to two different lines. And then this will just be this final conclusion here. Nice. So this is that. Now we have, so we're doing this second portion. We have f blah blah blah. Each of these Pn is integral as linear combination, etc., etc. Okay, show the final claim. So the final claim is we just want to show this, that we can pull this constant out. So we use we're just going to show equality on each piece of K projection. So we'll have, I'll have to put this in a line. So we'll have, for the first one, integral of sigma cf x dx. This is integral from 0 to 1. We have cf sigma t, sigma prime of t dt. And the next step is we want to actually do a projection. So once we do this, we can then pull this in, p sum k and once we've done that, we can use definition of Dirichlet product. So we'll have sum AB equaling K. We'll have our first projection will be A with C, and our next projection will be B with F sigma t times sigma prime of t. And then we can use linearity. So we just pull out this summation. And then we just have these projections. That's definitely going to be too much on one line. Yeah, for sure. Okay, so we start with this projection. We pull that through with this substitution. This right parenthesis should be inside the dt. Right there. And then separate that out with the summation notation for the product. We then have, we can then pull out this sum and these constants, and we can also pull out this projection of these things. But then this is just, we just have the solution here. This is just p sub k of c times this integral on sigma of f of x dx. And actually, let's set it up like that, I think. Let me also look over the other one. Hopefully this will fit. It does, okay. And then we just have this projection, so there's that. Since we have equivalents on each projection, they are equal. Oh, whoops. That was in the wrong spot. That should go right here. So there's linearity. So we've shown if we have two integrable functions and we add them, they'll be integrable, and these integration is additive. We've also shown that if we have a function with a non-zero constant, it's integrable over some contour if and only if c times f is integrable. And also we have this linearity. So integration is fully linear now, we've proven. Something else that will be useful, we should probably show integrability of products. And that's essentially going to be a similar way. So actually, this is technically a more general version of this, this first portion here. Actually, we can pretty much just copy this, actually. Pretty much, and that actually might let us simplify that a little bit. That's not what I wanted. Okay, there we go. Projection f of sigma t times g of sigma t, instead of doing c, since each of will have this and this. Finite sum of integrable functions. Since this applies for any k, f times g is integrable over sigma. And let's see what that looks like. Okay, not bad. So actually I'm going to take this whole theorem, I'm going to put this above the portion for multiplication by constants. I'm actually going to put this first. And then down here. So So this checks out. Nice. Okay, so we've got products. Products of integrable functions are integrable. Sums of integrable functions are integrable. And integration is fully linear, where a function is integrable if and only if itself times some non-zero constant is integrable. So that gives us full linearity. So we can make a note of that. So let's see what's next. So we have a whole bunch of theorems that we need to port over and prove. So our next one would be not quite this high, right around here. So what we want to do next, so we have a couple actually, now that I think of it. So we've got sums, we have this linearity, we have cancellation, we have, so we could do something like this if we wanted, where if we concatenate, yeah. So we've got a couple of claims here. I'll leave them for later. They're not quite as interesting. I think we don't need them yet. The ones that are interesting are these ones. So we can start talking about antiderivatives. So if a function has an antiderivative, or rather, any antiderivative for a function is an indefinite integral. So that's sort of what we're going to get into next. So let's do that. So consider a function f mapping S to A, or S is some domain. An for f, an antiderivative for f is any function f, the same domain, which is differentiable with derivative f prime equals f. We can instead say, let me think. So we want to have antiderivatives, and we want to have indefinite integral functions, right? Okay, so taking an antiderivative is the reverse operation for differentiation. So similarly, if f is integrable and indefinite integral function is any function f such that an indefinite integral function is any function capital F such that some path integral of f over sigma is just equal to this difference, capital F of sigma 1 minus capital F of sigma 0. So for any contour sigma over which f is integrable. So there's two different notions. So can say taking an interderivative is the reverse operation for differentiation, while let me reword that. We'll just have that there. In certain contexts, the two notions are interchangeable. That's what we want to lead up to. So we're going to have some theorems for that. So our first one we want if we have an antiderivative is also, so the integral of a derivative, so let f be integrable over sigma and have antiderivative capital F, then f is also an indefinite integral function. F mapping as A, have antiderivative F, then F is okay. So there we go, that's better. Okay, every antiderivative is also an indefinite integral function. Nice derivative. Okay, so the proof, so let f mapping SA, actually f and capital F be such that f capital F prime is lowercase f, and take any contour sigma over which f is integrable. Then we want to prove this identity. We want to show, let's see, so we can do this using the fundamental theorem of calculus. That's what I did the first time on each projection. Okay, so So we have integral of sigma f x dx we'll have f is actually, so this is p sub k. F is actually the derivative ddx of capital F, and we can also say, actually let's not do that quite yet. Let's say, let's pull this projection through. This is integral 0 to 1 of f of sigma of t times sigma prime of t, and we can instead say capital F if we would like capital F prime. And then we can pull this projection through. I might have to do a little more verbose in these steps. So we're going to do that, and we pull in through in the projection. This will be dt. Okay, yeah, so we apply this projection. We apply the substitution formula. We pull in this projection, p sub k. And then we want to say that this is just this p sub k projection of, we have ddt of f of sigma t. That's just literally what that is, or rather capital F. Okay, given that the dt is the real derivative and p sub k is linear, then we should have p sub k of the derivative is just the derivative of the p sub k projection. P sub k is linear, this thing is that, and then we should have so this will be so we had this, and we're going to pull in this p sub k, just like we said. And then by the fundamental theorem of calculus, this is just whatever this is at 0, or at 1 minus its value at 0. And then this is also, we can pull out, because p sub k is linear. Hopefully that looks nice. Okay, that's good. Right, okay, so given that this ddt is the real derivative, so it's just a limit of real fractions, and p sub k is real linear. P sub k of this derivative is just the derivative of p sub k. By the fundamental theorem of calculus, so we end up with, so this original term, this is equal to this whole integral, but we pull in, let me be more explicit about this. Oops. So we pull in this, this p sub k, like that. It's definitely gonna, yeah, pull over. So we have this is that, which is then this, and then we pull that through like that. We can also, instead of having some dialogue in the middle, we can put this whole thing in an align environment and then narrate it after the fact, and that'll help us a little bit to economize space. Space capitalism sounds terrible. I'm joking. Okay, so we've got this projection. We can pull this in through like that, and then with the substitution rule, rewrite the f prime. This is just this. If we would like, we could, if we were to be explicit about this, this would be 1, 2, so yeah, 1, 2, and then, hold on, wait, 1 for the substitution, 1 for pulling in the p sub k, and then 1 for pulling in f prime. So that would be another 2. We could do that, that's fine. That's not that big of a deal. It'll just be one extra thing. So we've got this. We'll rewrite this as, so we'll do right here, or rather, yeah, we'll do this whole expression, this f, put that out there, and then we pull in this piece of k while we're replacing f with capital F prime. It's definitely going to be way too long. Let me see if maybe that will help. It did. Okay. We could also pull off, instead of putting that right there, let's put this spacing the next one over, right there. Oh wait, right there. Ampersand, ampersand. Too much sand. Okay, great. Yeah, so so here we have the from the second line is justified by the chain rule, and the third line is justified from the fundamental theorem of calculus. Given that this ddt is the real derivative, p sub k is, hold on, we already have this. Just find from this. Hold on. Okay, so Let's actually rearrange these. So we should have piece of k with so pulling this p sub k projection with the ddt derivative is also justified from the fact that ddt is the real derivative and p sub k is linear. Since we have equality on every projection, again, this gives us equality in general. So this is essentially the proof. Every antiderivative is also an indefinite integral function. This does not prove necessarily that every indefinite integral function is an antiderivative, which is sort of what we want. That's another thing that would be very interesting to have. It doesn't generally work, actually. It depends on the domain. So here, we've proven this without any considerations for the domain S. It doesn't actually matter what S is. And essentially the reason that this happens is that we've defined an indefinite integral function in terms of paths, sigma. So for example, if a function is not integrable on any path, then it technically this definition doesn't include that case. I should probably add that because that's sort of a null condition. So we should say a function S is generally integrable when every contour sigma subset to S when it is integrable over every contour sigma subset to the domain. An antiderivative for such, or sorry, no, wait. That's not right. Let's rearrange so that this should be moved down here. Let's also, maybe this could be moved higher up. Okay. Yeah, we'll put this right down here. Actually, you can put this up here. Okay, let's edit that. So a function defined over the range of the curve. So we'll say F of S to A with sigma subset to S. F is defined on sigma, okay. We define a path integral, etc., etc. We also say f is considered to be generally integrable when it is integrable over every contour subset to its domain. Okay, nice. So that's integrability, blah blah blah, integral over sigma, products integrable. Okay, nice. Then we're down here, full linearity. An antiderivative for f is a function with its which is differentiable with derivative f prime equals f. So taking an antiderivative is a reverse operation for differentiation. F is integrable. An indefinite integral function is any function capital F such that this equality holds for any contour sigma over which f is integrable. These are sometimes interchangeable, so then we have our first proof. Every antiderivative is an indefinite integral function. And then the proof is just using, we have a substitution, we pull in the p sub k, we replace f prime, we use chain rule, and then we use this linearity of p sub k again with a derivative. Okay. So what we can do, if we would like, we can probably add a lemma. Maybe we will, maybe we won't. I'm going to leave it for now. Next what we want is wow, okay. So actually in my draft I have let's see. If we have an indefinite integral function, it's actually pretty fast. Although, actually, my draft uses a method that we don't have access to, as a matter of fact. Actually, it uses a method of differentiation that we haven't defined. Actually, though, this isn't necessary. We don't need to define this in this way. We don't. And the reason is, and this theorem actually proves a condition on this type of derivative we haven't proven, which is stronger than the type of derivative we have access to. So we should be able to repeat this theorem, actually, with the same basic structure. We just need this lemma. So this lemma is essentially what we're going to prove in just a second. The proof is just going to be essentially the same thing, really. We're going to prove essentially dominated convergence. So we want some uniformly bounded series of functions, so they're all bounded by some constant. And let's see, what is this other set here I've defined? This is C sub R. I think that is, I think I may have written that to be the set of functions with which are, oh gosh, I actually don't know. It's undefined. Great. That probably means it was a typo. That's okay. Because I can just go back another version once more. And we have another version of that theorem in the previous draft, which is much longer than the second one, even, which is still much longer than what we're working with now. So this should be, the actual statement is, so what we want to try to prove is the right dominant convergence. This. Okay, so we just have blah blah blah, sequence of functions, continuous on sigma, to limit pointwise to a continuous function, and are all bounded by some constant upper bound. So, uniformly bounded, integrable functions, which limit pointwise. Is that actually the condition that we have? No, we just have C sub r, which I don't know what that means. We could just say, so we do want to adapt this theorem, but we could just say that these are all continuous. Yeah, let's just go with it. So okay, so we'll do let f sub n sequence of functions and f be integrable over sigma, and let the f sub n be uniformly bounded and have f sub n goes to f pointwise, then the limit n to infinity of this integral over sigma f sub n of x dx. This is just integral over sigma of f of x dx. Alternatively, we could say, no, that's fine, yeah. That's not right, actually. There we go, that's better. Okay, that's cool. Nice. Okay, so So this is just basically dominated convergence. So since each projection piece of k sigma prime is piecewise continuous, then it is bounded. So sigma prime is bounded as well. Since follows that F the product F sub n of sigma of t times sigma prime of t is bounded across all n. So all of these projections are bounded, and then we just want to say, let's just take a projection of one of these. So we'll take, say, some piece of k projection, and we just want to apply, essentially we're going to apply dominated convergence theorem on every projection. So this will be, so we'll just use our substitution rule. So we have 0 to 1, Fn, sigma t, sigma prime of t dt, and then we pull in this projection piece of k. Then we just pull in this limit. Okay, so let's put this in a line, and we can sort of pull all of these out. This one, we'll start with this. And then we will end with pulling out this piece of k projection all the way to the front. Okay, so that would be, so for each k we have this projection of this limit, is this limit this projection, which is this limit of this integral, so we do this substitution rule. We pull in the limit by dominated convergence, and then we just pull out the projection again, and that is it. And actually, let's pull this equality here onto that first line, and put this one onto the second. Nice, okay, so the exchanging of the limit is justified by dominant convergence theorem. Oh yes, and then we should end this with we should undo the substitution. Also, this doesn't belong there. That should be on the outside now. And I think that is the whole proof. Sans some editing for visualization. So I should do this in reverse order, like I usually do. Because then it's more clear why this is valid. So I'll start with this. We'll go next to this. Then we will have this. Next we have this one. And this one. And then this. Hopefully I did that correctly. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. Perfect. That means I got them all. Okay, so we take this projection of this limit, which we know exists. We use substitution rule. We then pull in the projection. After that, we exchange the limit from dominated to convergence. We can then rewrite this inside. That's quite a mess. We pull out the projection. We should do that in 2 steps, maybe. That's quite a jump. So we have this limit. And we want to do this as limit blah blah blah. So you want to pull out the projection first. And then pull out the projection. Actually, you can pull this projection all the way out of the limit. And then this line can be omitted. Perfect. Right, so on the first line, all we do is we have this limit, we apply substitution rule, we pull in the projection, then we apply dominated convergence, then we pull the projection back out, and then undo substitution. Perfect, that's really succinct. Yeah. Okay, that's nice. So this is dominated convergence. So essentially, as long as we have these Fn all being bounded by some constant, and they limit to this thing, then we get the proof. Where, of course, in this case, bounded means each projection is bounded. So that's nice. Now, using this, so if we wanted to, we could probably, actually, we can actually probably put this before this other proof about antiderivatives and so on. And that might be a little more clear, I think, so that we sort of have both of these proofs in the same spot. Nice. Okay, so antiderivative is a function which is capital F, which is differentiable with derivative of f prime equals f. Taking an antiderivative is the reverse operation for differentiation. F is integrable. We can actually probably strike that sentence there. If f is integrable, an indefinite integral function is any function f such that integral across this contour has this relation for any contour sigma over h lowercase f is integrable. And we can also strike this sentence. So the first proof here, we have every antiderivative is an indefinite integral function for its derivative. The next proof that we want to say is oh, this only applies to open sets. That's unfortunate. I think that's okay. convex, actually. Okay. Yeah. I'm going to say F is integrable. Every indefinite integral function for F is also an antiderivative. Maybe. Okay, so the proof. So let F be an indefinite integral function for F. Given, so actually, maybe I should do that first. So and take some point x0 in S, then we shall show f prime, capital F prime at x0 is f of x. So since S, since our domain set S is locally convex, then there is a relative open set X in U subset to S. Relative open set X and U subset to S, which is convex. So U is a convex set, and then that means, so we can actually do right, okay, so this actually lets us define or we could do a lemma here. And say let F be S be path connected and F map S to A be integrable, and then for any two actually this is maybe not, well it's fine, any two indefinite integral functions f1 f2 over 4f, the difference f1 minus f2 is constant. Okay. Proof for this is super simple. And the proof for that is, since it's path connected, so we want to say, fix some point x0 in S, then for any point x in S, and there is a path sigma sub x connecting sigma 0 is x0 and sigma of 1 is x. Then we have f sub 1 of x minus f sub 1 of x0. This is this integral on sigma of f of, I should not use x, I should use x sub 1. x1 minus x0, sigma f of x, but this is just f sub 2 of x1 minus f 2 of x0, and this implies that 0, which is just this term minus this term which is just f sub, actually I guess this isn't really necessary, f sub 2, f sub 1 of x1 equals f sub 2. Oopsies. That is not correct. F sub 1 minus f sub 2 is equal to f sub 1 x0 minus f sub 2 x0. Let's speak on x actually might work. Or I could just make up a word and not define it. Sounds great. S be contour connected and F be integrable, any two indefinite integral functions, the difference is constant. 2 points, x0, x1, by so then done. Then you can find a door sigma in S connecting sigma 0 to x0, x sigma 1 to x1. Then we have this is that, which implies this difference is that difference. Oh, I'm a silly goose. I want to subtract f2 of x1. That's exactly what I did. Okay. Okay, cool. Okay, f is an indefinite integral, fix some point x there, blah blah blah. So since every, actually we can say fix some point x0 in S, then since S is locally convex, there's a relative open set which is convex. Since U is convex, then use contour connected. So every indefinite integral function agrees up to an additive constant. If we can show that any indefinite integral function is differentiable to f at x0, then they are. So we're going to use this lemma, this fact that the difference between two indefinite integrals is constant. The derivative of a constant is 0. So we're going to show that if we can find one indefinite integral that differentiates to f, then they will all do that. So we'll define capital F at x is defined as equaling, actually let's say x sub 1. This integral from the lower bound will be x0 up to x1 f of x dx. This is well defined since U is convex. X1 in U. Okay, so we just define essentially the indefinite integral function that we're going to use is just this capital F function. It's just for, we fix some point x0, and for each other point x1, we just take a straight line path and we just integrate across that straight line, and that's our indefinite integral function. Yes. So essentially this would also be considered f, some f0 of x1, f0 of x0. I guess we don't really need this lemma in that case. So let f be actually use f sub 0. indefinite integral function for f. Actually, then we can say for any x1, x0, define x1 in U. This will define since use for this, blah blah blah. If f is differentiable with capital F prime is lowercase f, then likewise f0 prime equals f, and the theorem is proven. So that's what we're going to do. So we're just going to show that this specific sort of integral function will be differentiable to f. So to prove that it's differentiable, you first apply substitution to pull the x0, x1 out of the bands of integration. So we'll have fx1. This is this integral, and we can actually say this is from 0 to 1, and the path is x0 plus t times x1 minus x0, and its derivative is x1 minus x0. That'll be dt. And then we can further pull out this to the front of the integral. And that gives us actually our difference quotient. Right? And then we just have to prove that the limit will converge. So we would be dividing by x1 minus x0 to prove that the limit converges. So I think I did something different. So what I did over here oh, interesting. I think I restricted continuous, perhaps, is required. Okay, so it definitely would be enough to assume it's continuous. Let me think if maybe there's any other way. For example, we could attempt well, that might not work. Okay, I think I know what it has to be. If it's integrable, I think what we can do, so without assuming that f is continuous, I think what we can do is we can say that using, or rather, since f is integrable, it should be bounded on any I want to say it has to be bounded. Maybe that's not enough. Maybe it does have to be continuous. I guess I'm just gonna add that into the I'm just gonna say it's continuous instead. Instead of saying it's integrable, which is stronger. This then gives us, put this in there, and then we'll be saying fx1 minus fx0 over x1 minus x0 is just this integral. And we can also say if we subtract f of x 0, that can be pulled into this integral just like that, because our integral has a weight of 1. And I'm also going to add some alignment here in the front, at least for these two. Maybe. Let me see what I want to do with the first one. No, let's not do that. Let's line up the equal signs instead. That one. And that one. Okay, I think that's probably better. Okay, so you have this, and we're saying this is this integral minus f of x0. That's too long. Oh, I guess I have to do it that way, the other way. Okay, so now we have this. So since f is continuous as x1 goes to, oh, maybe we could actually replace this x1 with y. Fix a point x0. Actually, we can just fix a point, yeah, fix a point x0. Blah, blah, blah. For any y, f of y is y minus x0. So be y, blah, blah. Fy, so we go from x0 to y, x0 to y. I'm just changing this x1 to a y label. so that's a little more familiar, I think, with the definition of derivative. Okay, I think that's all correct. Okay, nice. As y goes to x0, we have this expression. This thing go to 0. Actually, I can say this goes to x0. Right. So now that we have the difference quotient and we subtracted off what we expect the derivative to be, we just have to show that this right-hand side vanishes. So since f is continuous, we have f of this whole thing. I should say for each fixed t, we have this limit. So f of x0 plus this stuff, this goes to f of x0. This t just zeroes out this expression. So pointwise. So our integrand tends to 0 pointwise. Let me think. Right, so our integrand tends to 0 pointwise. To prove that the integral goes to 0, we can apply dominated convergence theorem. So what we want to do is say oh, I guess that's okay. Okay, let's select a sequence in advance first. So okay, so we're going to select a sequence of y sub n in advance. We're going to have this in our convex neighborhood without x0. And we're also going to have y sub n limit to x0. Then we notice, so since f is continuous, for each fixed t, we have this limit. So if we have y sub n here, this goes to f of x0. Or sorry, yeah. Regardless of what t is, we have y sub n going to x0, so this difference tends to 0. That goes to f of x0. So our integrand tends to 0 pointwise. Moreover, we also have, or rather we can say, if we let k be this set, so we can have x, the set of x0 union the set of all y sub n such that n is in natural, and k is sequentially compact and thus compact. So it follows that we have set of these, oh yeah, actually we can say naturally then the product k times the interval 0, 1 is also compact. So when considered as a function f which maps k times 0, 1 with f of y sub n comma t equaling, or rather than f, we can say g. Actually label my infinity as equaling x0, then we can consider g which maps the extended integers times 0, 1 as being this function. So we have g of y comma t equaling this thing, which is continuous since its domain is compact and g is continuous, then its image is also compact and therefore bounded. Wow, that's great. Okay. Okay, so what we're saying is, so we've got this difference quotient. So we're saying, in order to prove that every indefinite integral is an antiderivative, we're just going to prove it for this one specific indefinite integral function. So we set that up. So we set f of y is just this integral from x0, x0 to y of lowercase f. We do the substitution rule on this linear path for each y. We factor out this y minus x0, well this f of y, right, because f of x0 would be this integral from x0 to x0. That would just be 0. So this is actually, this f of y is actually f of y minus f of x0. We can now divide by this, so this gives us our difference quotient. And then we just have to show that this difference quotient tends to f of x0, lowercase f of x0. So we subtract our lowercase f of x0, and because this integral is over a 0, 1 range, when we subtract f of x0 on this right side, we can just pull it into the integral. Once we have that, now all we have to do is show that this integral on the right side goes to 0 as y goes to x0. So what we can do is we select any sequence y sub n tending to x0. Since f is continuous, for each fixed t, we have this integrand, we have this f, this function here going to f of x0, so our integrand tends to 0 pointwise. So that's just because, if we plug in x0 for y, this whole thing just reduces to 0, and then we have f of x0 minus f of x0, and that's 0. So the integrand tends to 0 pointwise. Furthermore, if we label y sub infinity as just being x0, we can consider a function g, which maps the extended integers, positive integers, multiple times the 0, 1 interval, as being this function g of y comma t is just this function f of x0 plus t of y sub n minus x0. That's literally just the integrand. Actually, I should have minus here, minus f of x0. Okay, so f is continuous, integrand tends to 0 pointwise. If we label y infinity this, we can consider g, this times that, as being this function, which is continuous. Since its domain is compact, and g is continuous, its domain is compact and g is continuous, then its image is also compact, and therefore bounded. So, since the integrand tends to 0 pointwise and is bounded across all t and n by dominated convergence, the interval vanishes. And then we can just state the conclusion, which is just put this down. Let's say this limit as y goes to x0 of this fraction is equal to this limit of that, which is actually, I could probably do this a little better. I probably don't need this line. This is that. Okay, very nice. So we have this limit of the integral is the integral of the limit, and this is just a constant. This is just f of x 0. And since the integral is over 0, 1, that's just f of x 0. Hopefully, that's a little long. Okay. Put that in an alignment environment so that we can do some new lines. Let's see, we have we'll just pull out close this thing. Okay, that's fine. Seems like that's all we need, so we're done. There we go. Okay, so what we've proven now is if we have a locally convex domain without isolated points, and our function is continuous, then its indefinite integral functions are also antiderivatives. Which is sort of the other version of the other direction of this theorem. That's really nice. So we have basically both fundamental theorems of calculus proven using the fundamental theorem of calculus, but in this higher context. So integral of the derivative is the function, and the derivative of the integral is also the function, subject to some conditions, like the function has to be continuous if it's inside the integral, in this case. And also, we may need our set to be locally convex. I think we will leave it there for now. So these are some nice proofs of all of these properties. Yes. Next time, we will keep doing integrals. I'm not sure exactly which theorems we'll be proving next time. Oh yeah, possibly some bounding things. Maybe also some path concatenation. That could be interesting. And we'll get more into, I think, path independence. But we'll see how that goes. We will see how that goes. Yes. This is interesting, though. So this essentially is showing us that if we have, path independent integration, if we have an indefinite integral function, then we have an antiderivative. And if we have an antiderivative, then we have path independent integration. We will have to, what we're going to have to do, I think, is we're going to have to find some conditions to show that differentiable functions in certain contexts do have path independent integrals. That will require certain restrictions. So we'll have to restrict our domains. So not every domain will have that property, for sure. In particular, there's plenty of cases where it doesn't apply if the domain is not simply connected. But that's going to get into a lot of complicated stuff. But we'll get into that when we get there. I'm going to. I think we're done for today. We got a lot done. There's actually quite a bit. In fact, more than I think I expected. 9, 10, 11 and a half, 3.5 pages. So that's pretty nice that we got through. Yeah, anyway, so thank you for joining me. I hope you found this interesting. Thank you. Yes. So I will be, yeah, so I'll be looking at, I think I'll probably leave these as they are for now. I'll probably do what I did last weekend, which is I'll work on, we'll keep going through these theorems, and then over the weekend I'll sort of, you know, fix up the wording or maybe separate different, you know, statements into lemmas. All in all, though, I think most of these proofs are pretty solid. Maybe just you know, add some better dialogue or something. But these are some nice proofs. Of course, as always, you can always check these in the read-only version of the link. That's always available. Yeah, anyway, so thank you for joining me. We will be going back at it again tomorrow, which will be May 25th, whenever I feel like it. Probably in the afternoon, almost certainly in the afternoon. But I will hopefully see you then. And goodbye for now.